This is where we left off in 5.2, and we're just going to be talking about Rolle's theorem a little bit more, but then we're going to get into the mean value theorem, which is more important than Rolle's theorem. But Rolle's theorem is a good precursor. And a real quick on this problem, while sine is continuous everywhere, just sine, and x plus 2 is continuous everywhere, the problem is when we divide, we have an issue, is we can never divide by 0. So x plus 2 cannot equal 0. So therefore, x cannot equal negative 2. That's part of our interval. So I would just leave it as g of x is not continuous. So therefore, it's also not differentiable. But you don't have to say both on the interval. So therefore, Rolle's theorem does not apply. And if you already watched, or already wrote this down from the answer key I shared, then maybe you need to just skip ahead to the next problem, which is us talking about the mean value theorem. So again, Rolle's theorem is a specific version of the mean value theorem. That's why I mentioned in the first video that the mean value theorem is more important. It's more dynamic. It's more of like Rolle's theorem is the appetizer, and mean value theorem is the actual meal. So just to give you a quick visual on this, because remember in the Rolle's theorem, the heights have to be the same. The y values have to be the same from A to B. Not the case here. In mean value theorem, they can be any height. And so as you draw a curve, just kind of draw a curve so it doesn't have to look like the one I had earlier. And I asked you for the secant, so I'm just changing colors. Then there must exist at least one point on that curve where the tangent line, so the slope at a point, is equal to the average rate of change. Now in the picture I drew, looks like there's a second one over here as well, but there must exist at least one. So as is typically in my nature, I'm going to steal from the answer key, so you get the formal definition. So again, we need a continuous interval, closed, must be differentiable on the open interval. And I know I wrote this in the first video, but there you go. Although I think I switched B and A around, but remember, but it's fine. F prime of C is equal to F of A minus F of B over A minus B. I typically write it the other way around. There must exist at least one value x equals C. So pause the video if you still need this. And I might even skip this first problem because the answer key is right here as well. Make sure that the function is continuous. And if it's undefined somewhere in that interval, then you can't do the mean value theorem. All right, so that'll save me a little bit of time as I go back to my notes. So in a problem like this, so again, you check the answer key on that one. So what about, all right, so we're still looking at this problem. This is the graph of H, by the way. Would the mean value theorem apply from 1 to 5? Well, you can even tell from x equals 1, looks like that's negative 2, to x equals 5, that for sure everything is defined on that interval. Give you a quick. So does the mean value theorem apply? Yes. What you want to double check is, well, I guess I could have done that in the previous problem, that the only undefined value was x equals 0. Well, 0 is not in that interval, So is it continuous on 1 to 5? Yes. Maybe a check mark. Is it differentiable on the open interval? Yes. So the mean value theorem applies. So if you were to look at that graph, and I already drew this, I was looking at that question actually next. It looks like the average rate of change from this point to this point. So if you were to actually do h of 5 minus h of 1 over 5 minus 1, graphically it looks like the average rate of change is up 1 over 1. And you could figure that out because if you were to find h of 5, and by the way, you don't have to just look at the graph. You can plug in 5 in for x. So 5 divided by 5 is 1. 3 minus 1 is 2, which matches that. And same thing with plugging in 1 in for that. 5 divided by 1 is 5. 3 minus 5 is negative 2. And 5 minus 1 is 4. Well, you get 4 divided by 4, which equals 1. So what that means, let me change colors, is somewhere in this on this graph, we have a tangent line who has a parallel slope to this. And I don't know where it is. It could be right here. Could be, it doesn't look like it's over here, but maybe it's right here. But somewhere on this curve, we have a slope that is up 1 over 1 as well. And that's what we're going to do here at the bottom, is we're actually going to apply the mean value theorem. So if I were you, I would rewrite that problem, h of x, from up here is 3 minus 5x to the negative 1 power. So then when I find the derivative, bring that negative 1 in front, be 5x to the negative 2nd power. Remember, the derivative of 3 is 0, and negative times a negative is positive. I would actually rewrite this as 5 over x squared. So somewhere on this interval, this derivative must equal this slope. That's what the mean value theorem says. So if I were solving this, I would go ahead and multiply the x squared over. And then to solve this, you would square root. Now remember, you do get two answers, plus or minus the square root of 5. But the only one inside of this interval is the positive one. And again, if I were to show you the answer key, he would write out only the positive and, well, the correct answer is only the positive, but he writes out C equals because of the way the directions are. But you don't have to write it that way. You can leave it as x equals because it's just a variable. We defined it as x earlier, so it doesn't matter. The square root of 5. And if you wanted to, you could round, hit the calculator, square root of 5, and then round to 3 decimal places. So as we look at the next one, and we've seen several problems like this. I think it was in 5.1 where we shifted down to, and you could actually look at a graph and examine this real quick, because this is continuous on this interval. If you cube root a negative, you do get a negative answer. Squared makes it back to being a positive. So this graph does look something like this. And a red flag should shout out at you, this is not differentiable. At x equals 0. I think you'd be fine if you talked about it's not differentiable on the open interval. And if you want more evidence, you could actually find the derivative, which is bringing that 2/3 in front. Subtract 1, it's now to the negative 1/3 power, which this is the same thing as 2 over 3 cube root of x. Well, right there is your evidence. The derivative does not exist when x equals 0. And so, therefore, the mean value theorem does not apply. Therefore, mean value theorem does not apply. And the next problem, it is important to make sure you justify the mean value theorem before actually doing this. And I'm aware in pre-calc we should have learned the graph of sine that looks something like this is differentiable everywhere. 2x is differentiable everywhere. 1 is differentiable everywhere. So therefore, the sum of all of those functions is also differentiable everywhere. So some sort of blanket statement that all polynomials and sine of x are differentiable, I'll just put a dot there, and continuous on its domain, which is the domain of these is all reals. And you could even write that out as you get into college math. We typically write that symbol for all reals. So we're good to move on. So what do we need to do? Switch colors. You find the derivative, which is 2. The derivative of sine is cosine. The derivative of 1 is 0. And you have to set it equal to the average rate of change. Now, some people will actually just write out or independently find the average rate of change, but you could actually work it out at the same time where, you do pi minus 0, that's subtracting your x's, and plugging in pi into the numerator. So 2 pi. As a reminder, pi on the unit circle is over here at -1, 0. So sine of 0 is 0. And then when you plug in 0 into the unit circle, as a reminder, sine of, 2 times 0 is 0. Let me put a minus here. Sine of 0 is still 0 plus 1. So these things will cancel. So we're looking at 2 pi divided by pi, which is just 2. So what are we talking about? Is we will have a point on this curve where cosine of x, well, when you subtract 2 over, will equal 0. So where does cosine equal 0? This point on the unit circle at pi over 2. And hopefully all of my work made sense there. If you needed to, you could probably independently figure out the slope, find the derivative, set those two values to equal to each other. Notice I subtracted 2 over to get this. And then I only wanted the one value bigger than 0 but smaller than pi, where cosine of x equals 0. And maybe my work would make more sense if I wrote it the way this person did. And again, I recognize that I don't like using C, but some teachers prefer it. Oh, I didn't even finish the problem now that I'm looking at it. I can go back and finish that. So the main thing that I'm looking at is this left side. And I'll just use his work. I'm not going to go back to my notes. If we're ever finding the equation of the tangent line, which I kind of jumped the gun and just found the mean value theorem, is you had to find the point at pi over 2. So your x-coordinate was pi over 2. When you plug that back into the problem, you end up with pi plus 2 as the y-coordinate. And I think you guys know me by now that what I would do is not leave this minus pi over 2 on this side. I would have added it over. And also notice that you found the slope of the tangent line earlier, and instead of redoing all that work, which he actually did, you already knew that answer, because that needs to be the slope of the tangent line needs to be equal to the average rate of change. That's the whole premise of the mean value theorem. And I don't remember if this last bit is in your notes, so I'll just go ahead and share it down here. So the mean value theorem guarantees that if a function is continuous on the closed interval, differentiable on the open interval, then there's guaranteed to exist a value c where the instantaneous rate of change is equal to the average rate of change on that interval. And you should be good to go for the homework.